And I start my yes, today we will be talking about rocket science, but not yet. So let me move quicker back. So we are in the module, theory module about learning on time series. So yesterday you heard some introductory information, some fundamental evaluation concepts. Today we will be talking about something which is called feature-free methods. So where you don't, well, at the end you do extract features, but you extract it in an implicit manner. So we will be talking about artificial neural networks and also about reservoir computing, and also about one of the state-of-the-art methods for extracting features actually from time series, which is called rocket and mini rocket. So nowadays, when you want to work with time series to build machine learning models, so you sooner or later come across mini rocket method. So that's what we'll be talking about today. But first and foremost, so we talk about learning on something which happens through some phenomenon that happens through time, and as such, I mean, this phenomenon it should take into account the causality. So what happens before certain events, if we want to classify it. So traditional feed-forward neural networks like multi-layer perceptron that we talked about a couple of weeks ago is unfit, as you can imagine. Why? Because you input all or you interface the entire input at once to a neural network. So then you train neural network to figure out the dependencies between different input features, but in this way, how you input it, so the network doesn't take into account the order of the things that happen that in time. So you need another approach to construct neural networks, and this approach is called recurrent neural networks, which schematically is illustrated here as its kind of basic building block. Then there are different recurrent neural networks which are different by the content of what is happening in this state box named, I indicated as A here in the figure. And the idea is that, well, as previously, you input some part of time series. Well, you take some part of a time series as an input, and you try to train a network to predict an output. So this is in the prediction mode, or maybe at the end you can build a classifier saying that it's the sequence belongs to one class or another. So I guess now the sharing has disappeared. Now it appeared again. Yeah, so what differs is how you interface your time series to a neural network, and it really depends on the task. So here I will not go into details of specific neural network types like LSTM, for example, or others, I'd rather resort to a general concept of working with data and put the focus more on something that you will work with in lab 3 instead. So here are the main training modes. Starting from 1-to-1, uh, uh, then if your task is about, for example, uh, image captioning, so that you have a fixed input, and then you want you want to train a sequence of tokens being output. So then this would be your training mode. So again, so one input, the blue boxes are output, and then there is a dependency between each subsequent token, so to say. In the classification mode, so if you want to classify, for example, sentences of text for sentiment analysis, or there are time series data sets, so you have a certain time series that belong to different number of classes. Again, you will work with one of them in the in lab 3. Or no, in the mini project, sorry. So then that would be the training mode. So you input your sequence, so one step at a time, and so on each new step, so you add the state of um, uh, the previous state of the network and mix it up with a new input and a new one, and at the end, so the output from the last step is mapped to a category, basically. Many to many. So when you have some buffer, so you scan a sequence, and then after some delay, you start to generate something. Many to many modes, or without this delay. In all cases, so that is the way how you construct your pipeline. But the main formula for recurrent neural networks is this. So basically, you have some nonlinearity. You remember, very often you use hyperbolic tangents, and so the recurrency here is about so taking the previous parameters of the network and mixing it with the new input. So that's this subscript T is responsible for. So in concrete terms, so this main equation is translated into this tonnage form. So you have matrix of weights, so matrix of neurons and weights of connections. And so whatever activations you take, you mix in the input signal, which is also passed through some weight matrix. And at the end, you project the final state of your network via this projection matrix to the desired to the output, to the target. So, I mean, on this level of explanation, it's pretty much straightforward. So this again, so you even visually what you see here, you have an input which is a signal. So it varies in time. So you take well, you quantize it, so you can transform from say continuous to discrete case, and you sample the signal in time. And so you enter the signal like sample by sample. And on any step, so the network takes into account the previous steps via this feedback arrow over here. And when you're done with the processing of a sequence, the final layer, and why it is layer, because here we have a matrix multiplication. So it outputs to specific to the target output. And as I said, so the target outputs, it can take different form. So depending on the case you have. But the question to you, I mean, this is pretty much straightforward formulation. So how to train this network? I mean, you remember when we talked about backprop? There it was rather straightforward. So there is a forward path. So you compute the gradients. So you reach the final layer. You compute the loss function. And by the loss function, you compute well, you actually compute the gradients and backpropagate them. So to adjust the weights of this matrix. But now, I mean, we have other connections. We have connections to themselves. So neurons are connected to themselves. I mean, how to go around it? In essence, what is happening is that you roll out this recurrent neural network structure into a feed-forward structure, more or less. So because so you take some first inputs, some initial random state of a network. So you have weights of this network. You connect it to, well, yet another network with a new input, and etc. etc. And at some points you have this outputs depending on the mode, on the training mode you have. So here you have many weight matrices to train. Yes, and here you collect all the losses into into a single loss functional. So what you do here, you basically apply backpropagation through time. So when unrolling, so you get a feed-forward network, and then you try to propagate the gradients back. So it looks more or less like this. So, and I mean, this structure can be very complex or very large, so that in order to optimize the process, one can also apply kind of batch or training on chunks of sequence. So in this case, we're talking about truncated backpropagation through time. So you take a part of a sequence, you train it, and then you take another part of a sequence and another part of a sequence. One of the problems with recurrent neural networks, because of this structure, the way how you actually roll out the computational graph is a problem with gradients. So it is possible that many gradients for this weight matrices become zero. So they well, actually either become zero or explode. So they become very large. So neither of the cases is good for training, as you understand. So your weight update should take very small values to find a minima. But again, the problem here is not in the training procedure itself, but rather in the complicated, complex nature of a loss function for a time varying signal. So it's not kind of not necessarily that it can be modeled by convex loss function. So the loss function can be very complicated, and so this vanishing gradient stuff is because of well, difficulty to choose correct good loss function amongst others. So there are some steps you can take to mitigate this problem. I leave it for your self study. Instead, I want to focus on other types of methods. So first, I want to talk about the state-of-the-art methods for um, uh, extracting or neural way of extracting features. And secondly, about echo-state networks. The common thing to both approaches is that extracting representation of signals is decoupled from the downstream task. So you can use same extracted features to train multiple models depending on what you want to do, multiple classification models, prediction models, etc. So first, I want to talk about these techniques called rocket and mini rocket. So actually, both are about the same. So the second one, mini rocket, is an improvement over the first one. So it is invented by the same set of authors from Australia, and as you will see, there is a nice kind of move to dramatically improve the efficiency, computational efficiency, because at the end, again, all the time the bottleneck is processing, so computational complexity of the methods. So, but what we'll do is kind of illustrate it on this sketch a little bit. So we will somehow process our time series. So we have a time series, a certain chunk, and we want to extract a descriptor, a representation of this chunk, which somehow characterizes it and makes it distinct from other signals belonging to a different category. And so the main concepts that will be used here are four. Convolution, proportion of positive values, dilation, and bias sampling. Well, that's the last one is specific to mini rocket, but nevertheless, convolution. It's pretty much same idea as behind convolutional neural networks, this convolutional layer in CNNs. So you have a sequence, so basically a sequence of values, and you have a sliding window, which you scan through this sequence. And this window is actually a set of weights. So you compute the convolution. So you do a dot product basically of the original values with the convolutional filter. So that's would be the keyword. We will come back to PPV concept later on, but the important one important concept would be dilation. Dilation is, I mean, in simple words, is a sparsity is the interval of looking at your samples. So you can look at each sample, so you like sequentially. So if you have samples 1, 2, 3, 4, 5, 6, so you take them in the order they as they appear, all of them, 6 samples. Huh? Well, sampling frequency. Yes, it is sampling frequency, but what I mean now is just um, yeah. Well, I mean, you can use it synonymous to dilation as well, but I mean, to me, when I hear sampling frequency is the way how you sample original signal. So you have a signal and you need to sample it with the proper frequency so that it is twice the bandwidth, this Nyquist frequency. So that for me, this it has this different meaning. Here we already have samples, which is sampled with the proper sampling frequency. And there are different ways of working with these samples now. So if you say dilation 1, so it means that you take each and every sample in the sequence, so sequentially. If you say dilation 2, so it means that you take every second sample. So dilation 3, every third sample, etc. So you look on different scales. So it's a scale of looking at your sequence. Okay. Yes. So let's walk through main items first for the rocket itself. So and see what's the difference to mini rocket. So you start with generating random filters, convolutional filters of certain length. Let's take as an example this configuration. So we have a filter with length 5, or a kernel filter. Kernel does we can use it interchangeably, and a dilation of 3. So here is our time series x0 through x12 and further, and with the dilation 3, it means that we take every third sample. So x0, x3, x6, and so on and so forth. So that's the dilation. And we compute the convolution, as I said, as a dot product between the weights of your kernel and the corresponding sample. And then you have you have now a shorter sequence, obviously. So of these values of the dot products. Mm. So what Mini Rocket does, so it has many this kernels. So it all these kernels applied on the same sequence, and then you need to do something with all these computed dot products. So what they do this pooling. So they from each sequence of computed convolutions, so they select a maximum value. Mm? And now we come to this proportion of positive values. Which is so out of all Uh, um, oh, sorry. So you have different you have many kernels, and for each kernel, you compute convolutions with the proper with particular dilation, so with the sliding window, so for the whole sequence. Out of all these numbers, for each kernel, you select the maximum one. So that is pooling. And then you have number of this convolution results equals to the number of uh, kernels actually. And what you do, so that would be your CIs. So now you have this vector of CIs, computed convolutions, but you want to select a single number of it, so which is um, uh, um, number of positive positive convolutional results. And then you have this array of or a tuple of maximum value and proportion of positive values per kernel. Now let's iterate it how you understand it. I think my wording was could be a little bit confusing. So how do you understand it? So can you kind of say it in your own words?
For the time series,
Yes.
with eight different kernels,
Yes.
and each kernel has its own dilation, which is how we use, let's say, sample the values inside. And then we apply the kernel with convolution.
So first we talk about a single kernel. Yes.
We apply the kernel, the time series, using convolution.
And sliding window. So we basically slide it with this dilation. So yes, okay, through the and we get an array of these C values.
Get by applying different kernels.
No, before that. So on this from this array of C values, you compute two numbers.
Yeah.
So one which is the maximum of these C values for a single kernel, and another one with the number of the proportion of positive values, because these values could be negative and positive. Okay. And for a single kernel, when sliding through the entire sequence, at the end you get two values. You have to compute, yes, you have to compute both. Through each and every sequence. So you have sequence 1, sequence 2, sequence 3. So we first focus on a single sequence. So and a single kernel or filter, whatever. So you choose a dilation and you start to slide through your sequence and compute convolution. So that's an array of C zeros to the number of strides, basically. And from this array, you extract two numbers, so max and PPV. So, and now you have 10,000 of such kernels. 10,000 of such kernels, and in total 20,000 pairs. And that all together, so put together, is a descriptor of your time series of a specific of a particular sequence. And as you can imagine, it's quite a lot of computations. But what you do here, and I think as part of the algorithm, so you vary. So the kernels well, kernels are generated randomly, and the dilation is also varied, and then also some bias varied. But what you get, you get a kind of distribution of reaction of your sequence to these random kernels, and so so putting them all together, then it's a kind of cumulative distribution stuff. So which describes dependencies in time in the specific time series. So that is about Rocket. So what you can do, so now, but again, as soon as you get it, so this is your vector. And as any vector, a vector of features, basically, and as any vector, now you can enter it into your model. Model can be any, and somehow I'm again. So I understand the need for learning, and in many cases there is a need for learning, but in some tasks you can get away with conscious encoding. And the good thing of it is that so these descriptors, they are task agnostic. So you can obviously train any model on the same descriptors. While if you compare it to I will not roll back the presentation. If you compare it to the training of recurrent neural networks, so the representations inside this, I mean, obtained through backpropagation, it's really specific to the task you learn. So you always learn task-specific representation.
So this is like training the description of the data set instead of using the data set for training?
Yeah, so it's a transformation of your data set into another form, which is a vector form. Yes. Uh-huh. So back in 2020, so this method demonstrated state-of-the-art results on classification of or prediction of on time series. So there are benchmarks. I will demonstrate this data set later on which you can basically test your algorithm. So that was the best one back in 2020. But as you can imagine, so all these operations to compute 10,000 features for a single vector, so it's very heavy. I mean, and not very scalable for large data sets. And then a couple of years later, so they come up with something which is called the mini rocket, which is a kind of heavily speeded up version of rocket. And mini rocket is, I mean, you can find it in libraries, so it works very well. So let me scan through mini rocket first. And I will also tell you what we did together with my colleagues further on. So now we maybe focus on classification tasks. So we have this time series, and we want to classify it to one or another category. So in mini rocket, so if you look inside, so what was the principle is pretty much similar. So you want to have kernels randomly defined, but so the principles of rocket should be preserved, but it should be faster. And they come with an interesting solution. So the kernel weights, the filters. So instead of being randomly generated from normal distribution, for example, So they generated a sequence of minus ones and twos. So like pretty much binary stuff. And you will see now why it is so. So it's two numbers, minus one and two. And then so they generate 84 of them, and the length is fixed. So so you don't need very large kernels actually. So and what they do, roughly speaking, is that they change multiplication operation, or they found a way to substitute multiplication operation in computing convolution. So computing convolution involves multiplication and summation. So they found a way to substitute it with addition only. And actually, speaking of in general about machine learning, so lots of research happens in really numerical optimization. So how to implement certain functions in a more efficient way. So this is one of it, which is interesting. So again, our dilation. So there will be different dilations applied. And what they do, so they, I mean, for computation of convolutions, so they define or they convert the original sequence into two sequences. So one which with the inverted sign, and another one which is 3 multiplied by 3. So each value multiplied by 3. So what you have to do before that, of course, you pre-process your sequence. I mean, so your values should be pre-processed as pretty much in a standard way. So here, what you do, you take you compute multiple of 3 and inverse the sign. So what? Oh, sorry. And then they basically they change the computation of convolution with multiplication of every number and summation into something. So let me just maybe I find. Don't I have the final formula here? Unfortunately, I think I deleted it somehow. That's very unfortunate. I think I see. Let me see. No. I think it is here. So you remember that the weights are minus 1 and 2. So basically. Yes, right. So this is the formula. So for the convolution, so they take convolution for the sign inverted sequence of for a given kernel. So this is just a summation. So you just sum whatever is in there, and then you add this G stream, which is triple or 3 times the original one at the positions where kernel equals to 2. So what happens is that I mean. So here you have the inverted sign. here it is 3 times stuff. So I mean, when adding this together, so it I mean it will end up in a value of 2. So I mean you can try that at home, but again, so maybe it's not very important to remember all these tiny details, but at the end. Having the same principles, so mini rocket works like tens of times faster compared to rocket, still having the state-of-the-art results. So then there are some details on how so they still for each kernel they produce array of convolution values, and so then what they do so they need to so for each kernel they need to come up with particular values which are PPV essentially. And for this, so they sample the resulting convolutional array for values with certain thresholds. And then they extract a proportion of positive values based on this subsampling. But again, at the end, they also come up with 10,000, with the high dimensional vector of features. And as with as any vector of features, so I mean, you can now link to what we discussed in the blog when we talked about vector symbolic stuff. You can do some interesting stuff in this high dimensional space. For example, so let's now switch gears to some more or less trivial example. But probably before that, so let's take a leg stretcher and so not to mix up the context. So a short break. So speaking of a rocket and mini rocket, I want to show you a couple of, one article here, so which kind of connects the content of today's class to what we talked about previously with respect to hyperdimensional computing, so distributed representation. So this work is from my colleagues in Germany, and so they suggested modification to mini rockets, which incorporates encoding of explicit encoding of timestamps. So when doing the convolutions. So I will not go into details. So that's kind of more of an additional extra information. But so what you can do with this, and this is done in a way how we discussed previously. So if you have a vector at some point, so the descriptor, you can bind it with the randomly generated vector which denote or which encodes a position, so the position in time tick. So you also incorporate the information on how this descriptors were constructed at each time point. Which kind of introduce extra information about dependence between different parts of the time series. So I will link this article in Canvas. So it further boosts the performance of mini rockets. So you can use it as a very useful tool. So, but we continue basically, and we now go into somewhat more complex case, which is a multivariate time series processing. So what is it about? It's about having several sensors, several channels that produce time series. So it can be well, two accelerometer sensors deployed at different places. Well, you can switch your imagination and construct your own example. So what we learned so far with Rocket Mini Rocket, so we got a descriptor of a time series. So you have a single sensor, produce a stream of data, and we can very quickly get a vector describing this time series. So, but now in our case, we have several sensors. Some sensors are well, maybe measuring similar modality, like a temperature or humidity. Other sensors measure other modality. We can have many sensors. We can have 100 sensors. We can have 2 or 100. In either case, we have 100 descriptors of them. So, but still, we want to classify. So we want to say that collectively, all these sensors correspond to category A or category B. So how to go around this case? I mentioned it several times. In neural networks, whenever there is a need to collapse representations from several layers, you use a superposition, so a summation of representation. So that you can find these operations you can find, for example, in transformers, so in other neural architectures as well. So you can sum them up. Or basically before summing up, so you can concatenate. So concatenation, for example, so that's what happens in transformers when after the attention mechanism. So you have multiple attention heads. So each spits out its representation, and they are stacked on each other and form a longer vector. So here is same idea. So you get these representations and you stack them upon themselves. The problem here is really the dimensionality. The higher is the dimensionality, the more complex is your model. So it's really an issue if you. I guess you tried already self-organizing maps, right? Or yes, good. So did you see how complication. Increasing complexity of the model results in the time in the training time. So yeah, sometimes you can feel that okay, this thing hanged, but it really processing time grows. Well, in some cases exponential with increase of dimensionality of the model. So here is same argument. So concatenating works. It works on smaller dimensionalities, like in attention networks, in transformers. So it works because they work with smaller descriptors or embeddings. What other options exist? So you can add them together. So that's also, as I said, one of the possibilities. However, I don't think if I mentioned it last time, but this is connected to the mathematical properties of vectors on given dimensionalities. So basically, when you add many things into a single representation, so after a certain number of additions, your resulting representation become too noisy. So too noisy with respect to, say, cosine similarity with vectors that you add together. And that is bad because, I mean, at the end, you come up with only a noisy vector, so which you cannot use for any good purposes. So, so in simple words, it leads to a loss of information, and especially when the number of channels grows. But then also, in many cases, you want to have some explainability. So not all of your time series contribute equally to the classification. So you want somehow suppress those less important and maybe highlight those more important. So here you cannot do that. So that's what are the main challenges to solve. So what we can do, so what is... I took this animation from Kenny, I mean, who visited me a couple of years ago. So what we want to do, we want to create a representation of each channel which is distinguishable, so which is kind of unique. And then when we superimpose them all together, so you can preserve this uniqueness even in the superposition, and for this we will be we will create tags for each channel, so of the same dimensionality as the embedding, and basically we will apply this tag to each embedding by multiplication, so or as I introduced earlier, binding. So at the end, you will get descriptors which are channel specific. So you even if you have so what I mean here is that even if you have two time series coming from a sensor, so a sensor of the same modality, say temperature, so they still will have very distinct descriptors, so they will not be similar to each other, and this is important for distinguishability or separability, improving separability properties. Yes, so that's what we did. So we created all these tags and we applied to mini-rocket embeddings for each channel, and now we want to superimpose them so into a single embedding. But we also want to again to suppress those channels that do not lead to good classification. So what we did, so we developed a neural pipeline, so a simple shallow multilayer perceptron that is trained on sequence of embeddings. And what we learned the weight of each embedding. So it's not a single input that we are interested as, for example, I described for the backprop network, but the weight of the entire descriptor or embedding. And here is the architecture so that we used. so we in Torch framework, so you can I mean you just overload the forward path. So and again, so you just say that don't modify, so treat these descriptors as atomic entities. Don't modify their coordinates. Rather modify the weights for each descriptor. And the idea here again, so it was very shallow network, and with normal cross entropy and trained for some classification paths. The idea was not to train it until kind of best result, but just to see the trend of improving, seeing which of the channels are which of the weights of the channels going to or are decreasing compared to the original values. And then what we do, so when we understand it, so we interrupt the training, and we simply suppress this channel. So we exclude them from the superposition, and that again leads to further improvements of the results. So here is the demonstration of what is the effect. So it's a made up synthetic data. So you have one valid channel, and then you have basically some noise sequences that are I mean and then you vary the number of channels. If you just use concatenation, so you basically don't you don't define the significance of this channel, so the classification accuracy drops significantly. So if you pre-train on the descriptors, so then potentially you can get significant improvement, and that's what we tested actually on this standard data set. So this is a benchmark for multivariate time series UEA data sets from time series classification benchmark. So if you Google, you can find these benchmarks. There are quite many data sets. Well, 13 in particular, with different number of channels. So here they are sorted by the number of channels. So some of the data sets have thousands of channels. Some others have just 2. But and here is what you can see what you can achieve. So this is the so this column is the concatenation. This is just plain superposition. So you see the effect of just smashing together. So especially for the large number of channels, so you see a significant decrease in performance, versus pre-training and understanding which channel is more significant and excluding it from the superposition. So all in all, what is important here is my message here is that if you in applied AI, so if you want to build a solution, you really need to be maybe creative in choosing the methods. First, I'm a big kind of fan of learning free methods but still neural methods like convolutional methods for extracting descriptors of feature vectors. But then because these representations become task agnostic. So, and in many cases, so you can apply vector transformation methods, like I described this random Fourier features, to improve separability between classes. And the most important thing is that you can use simpler models. So you can train regression. So we will be talking about regression now when talking about echo state networks. So linear models are simpler, and at the end, so your solution can be much more efficient, computationally efficient. So let us switch gears towards echo state networks and reservoir computing. So this is a neural network architecture, but not any neural network whatsoever network architecture. It is a very special one. It is based on the concept of computing with randomness, and I hope you will see the kind of strength of this model when working with Lab 3. So I just briefly mentioned for a single purpose of mentioning it here, I mentioned problems with traditional recurrent neural networks. So the network architectures become bulky, so you have problems with the gradient propagation, back propagation in time. Slow convergence and all these issues with gradient. So reservoir computing is a different paradigm. It still has this ideology of recurrent neural networks, but it uses a completely different principle. So in reservoir computing, so the major shift of paradigm is the separation of the nonlinear part, so the recurrent neural network operation, and the and transforming the state of this recurrent neural networks, recurrent neural network, into an output by special transformation, so post factum transformation. So this transformation is not part of learning of weights. So the weights are modified non-linearly, independently on this final transformation. So here is the schematic. So that's what you will implement on Lab 3. So what you have here is U of n. U of n is your several channels. So those are, so you can see each circle here as its own channel, so time series or time samples, and they are projected by matrix W in onto dimensionality of a reservoir, which is W hat. So we will talk about update rule for the reservoir. So for each step, so you should now have this kind of backflash to this recurrent neural network formula. So it will take the previous state of this network. So this is a neural network, and in-bake the new input into it. And it will do it for all the steps, and yet not being kind of affected by what will be the output. So computing the output is a separate business here. But at the end, so we want to kind of extract information which is necessary for computing the output. So what we want to have from this network. What can it be? It can be a label. So it's class 1 or class 2. It can be next value in a sequence. So for example, you train your this network on a sinusoid for some time. So you stop training. So you want that the network predicts the next value depending on the current one. So you have a feedback. So in this case, then this network will work as a generator. So depending on the task, so this yn could be different, but in all cases, what you want to minimize root mean square error of the actual input output of this construct and the desired output. So your target. So let's have a look at the question. So now I hope you can see what is going on. So let us look first at this equation x tilde. So what it does, it takes it takes input. So it can be either a single time series or several. Plus one bias channel, and again, so by multiplication with W in, so you expand it to this to the dimension of the reservoir, to the number of neurons you have in your reservoir. And at the same time, so this x is your state of neurons in your neural network. So you take your previous state of neurons and in-bake it into the new input passing through the weight matrix W. So these matrices are generated once randomly and not modified. So they are not learnable. So we will see what is learning here very soon. And then, well, what is learning here? So we will learn this matrix that transforms the input and the current and the state of your network for this input into the desired output. Are you with me here? More or less. So here is the again training process. So you generate random reservoir, and again you see, I mean, you may approach this understanding of this method by purely from the mathematical formulation. So so you have matrix based transformations of input via some latent representation, so to say. So if it helps, I don't know if it doesn't distract your understanding. So first you have some latent representation, so which is in this case depicted as a neural network of certain dimensionality. And this latent representation modifies every time at every time step. So you have a new incarnation of it, which is governed by this matrix over here. And yeah, and then you take your training input, you project it with the W in and record. You really save the state of your reservoir. So after computing this formula over here. So by the way, I didn't mention. So this alpha here is a leak parameter. So in many cases, I mean, you should be you should do well without it or setting it to 1. so you don't so you just use the main update formula over here. So the recurrency is already in-baked in this one, so you don't need to kind of add the memory of previous activations. And when you process your input, so step by step, or sample by sample, and recorded this X, so which is computed by that formula, then you take this bunch of X's, so that this latent representation, so to say, and compute or learn the output transformation. So how to take this representations and transform it to a desired output. Yeah. So what you do essentially here with transformation, you do two things. You non-linearly expand your input to high-dimensional space, but also you, by the virtue of update, you implement a memory. So a fade in memory. So the more, so you will have some information from recent entries and some small information about samples in the past. For this, you need, I mean, this reservoir matrix should have a special form. So basically, it needs to satisfy echo-state property. So what does it mean? Echo-state property means that, again, so this is mathematical term, but the spectral radius of this matrix W should be less than 1. So this W over here, that actually, let me ask you, so what is, how do you interpret this matrix? So what is the meaning of it?
The evolution matrix for a system, so if it doesn't eigenvalues.
No, but I mean just matrix. I mean, so W. So what is W for you? So what is its physical meaning? Or in meaning in terms of neural networks? It's a connectivity matrix, right? W is a connectivity matrix. If you have 1,000 neurons at your possession, you want to encode which neuron is connected to which. So neuron 1 connected to neuron 5, and here you even allow that neuron can be connected to itself, right? So it's a recurrent neural network. So it's not a feed forward. So in feed forward the matrix is different, but so W, so it's a square matrix of the number of neurons to number of neurons, which is and each entry is the weight with which each neuron is connected to another neuron. And initially you generate it randomly. But now we're coming to what you say. So, I mean, randomly is okay, but you need to have some special property because, I mean, which manifests when you actually apply it several times, these modifications. And this special property, echo-state property, is about spectral radius of this matrix. What the spectral radius is, again, so it's basically normalization to the largest eigenvalue. Okay, so you have singular value decomposition stuff. So the vectors, eigenvectors and eigenvalues, so you read it on the side. So you need to, you can compute this characteristics of, so it's essential, capturing essential properties of a matrix. And you adjust your matrix to this value. So I will show you the code later on. So here again, so all you will read in this tutorial. So I mean, this is just a summary. Obviously, your parameter, one of the hyperparameter is the number of neurons. So larger number of neurons, so larger is the representation space. But then also sparsity. So I mean, you need in many cases you don't need full mesh connections. So you want to basically have this connectivity rather sparse. Yes, leaking rate, I commented on it, input scaling. Yeah, so that's, I mean, all these requirements are basically stem from purely from mathematical properties of computation. So to avoid some extreme cases. And then so when you constructed this W, you adjusted its spectral radius. When you chose the projection matrix, so from the low dimensional input to this dimensionality of your neural network, and you did this procedure so that for each sample, so you kind of incorporate it into the previous state of the network itself using the update equation. And you basically have number of reservoir states or neural network states. So it's kind of snapshots. So as many snapshots as the time steps. So you take, so now you want to compute the transformation to the desired output. And this is you do by learning the V out, W out matrix. And what is interesting is that this learning, well, you can imagine probably learning using different strategies, but apparently you can get away with linear models. So you can learn this matrix with Ridge regression. And here is again is a formula. So well, I don't know well, Ridge regression is a valid learning method. So you take the vector of output, so what depending on the use case. And X is your matrix of recorded reservoir states. So it will be basically the number. So the dimensionality of this matrix will be what? Tell me. The dimensionality of the reservoir by the number of time steps. So it won't. It will be this rectangular matrix. So where you record, well, depending on how you look at it, but yeah. So this will be your matrix X. So you can transform, transpose it. Obviously, I mean, transpose may not exist. So you do this pseudo inverse here, and yeah, and basically complete learning by computing it. Yes. Are you with me here? So once trained, so now the whole now your training is done. So what you do now, so you again for a new time series, you repeat the input steps. So you project it to reservoir, record. You take you compute X matrix, and now you have pre-computed V out. You just do matrix multiplication, and you get your output as a result. And it is here where So with this ridge regression where the square root mean square error is taken care of, I mean minimization of it. The last thing I want to comment on, normally questions arise about it. The usage of feedback. This is the case where you don't want to classify, maybe, but you want to make a generator, as I said. So you want your network be able to feed in the output into the reservoir, so as an input. And how to do that? So I mean, if you think about it, so that's not obvious. I mean, this yn appears only after you train this V out. So I mean, there is no basically yn in the training loop. Yes.
But then the reservoir size shouldn't be bigger, like instead of x of n should be x of n plus input.
Say again.
The reservoir, you see, you have the function that is x of n.
N is a number of
But
times.
and if the number of inputs, shouldn't it be bigger?
No. N here is it refers to time step. So if you have n time steps, then it's so it's a value of x on step n. So what you do here, so you want to kind of feedback the output, but for training purposes, what you do, so you should have the ground truth, so the clean value, the true value. So you don't know the prediction yet, but you have clean values, so like true value of sinus, for example, and that's what you feed in there. So you feed in the target. So you basically treat target as yet another input, but projected using different projection methods. So that's the catch. But in the inference phase, that will be the true input. So that your network works as a generator. Also, I didn't tell, but I mean, you can imagine the case that I mean, this network can be used as a controller. Why? So I mean, one of the input can be the knob to switch on or switch off the certain behavior of the network. So I mean, for example, outputting sinusoid with a different frequency. So you would train it for one input signal. So it should be like with one frequency, and then when you turn the knob, it can be with another one. So it's very powerful thing, I would say, and yet no backprop. So not everything is backprop. So that's my message, and I hope you will enjoy programming it. So that's what you do, how you apply the teacher forcing stuff. Yes, so basically the last thing, so now I overshot 1 minute. So these are the hyperparameters. You do this grid search, so the normal stuff. So it's a tedious process of training. So until you are happy with hyperparameters. So those are these ones. And here are some recommendations on how to, I mean, in what sequence to approach training of reservoir. So all the rest you will discover yourself. So and again, for the record in Zoom, I hope did I start recording? I hope. I want that this lab you do without any libraries. I mean, so you need to implement it by the book, so to say. So you are given this practical guide, and you need to implement all the steps yourself, not picking into ChatGPT. When you do it, so you will see how, I mean, you will suffer through this process, but I think it will be rewarding if it will work. All right, so that's it. Any question? Yes. Yes.
The task is to like present this article and another article based on the first article. And then we have to choose the time when we want.
Yes.
When do we have to choose it? And when-
As soon as possible, I will send a message today, max tomorrow, with instructions. Also on Friday, and those how many? We have 7 people in Zoom. I spread this message to all. On Friday, I invited people from a company. So they doing machine learning for fraud detection. Very interesting. So if you want to hear some applied aspects, so Friday 1 p.m. So I hope to see some more people, more faces. Okay, good. See you on Friday.
I have a question.
Yes, sure.
We haven't really received anything about the seminars, so
I just said that within, I mean, today or tomorrow you will get detailed instructions.
okay.
Yeah.
That was it.
Anything else?
No.
Okay. Good, but please come next time to the class on Friday. Okay. See you. Bye bye.
Mine,
Bye.
yeah.